Hello, everybody, and welcome to this month's Footsteps to Mars Hangout. My name is Tony Darnell, and I'll be your host and/or moderator. Maybe both, maybe one or the other. Depends on how I feel. I don't know. Anyway, I want to welcome you guys this month. We are going to be talking about Curiosity, rovers, and other things in orbit around the surface or around the planet Mars. And in particular, we're going to be taking a look at how these efforts are helping us actually put human beings on Mars. So if you don't know what this is, and this is a pretty new series, this is only our second one, where we are talking, this is a monthly hangout, first Friday of every month, so mark your calendars, where we're going to be taking a look and talking with scientists and engineers who are both from the American Astronomical Society and the American Astronautical Society. These are members of both organizations who help us get to Mars. They're either working on stuff to get us there, they're studying the planet to find out what we need to know to get there, and all aspects. And so we're going to be bringing that to you each month. So that's what we're doing. And today, on this 40th anniversary year of the Viking landing on Mars, we're going to be taking a look at rovers. I can't believe it's been 40 years since Viking's been there. I feel really, really old. But before I introduce my guests, let me introduce my co-host, Dr. Harley Thronson. He is an astronomer and astrophysicist at NASA's Goddard Space Flight Center. Hi, Harley. Welcome.
Good to be here as ever, Tony.
Yes, it's great. Thank you.
It's going to be a great duo we've got.
I know. I'm looking forward to it. Ordinarily, our good friend Alberto Conti joins us, but he was on travel and couldn't make this hangout, but he will join us next month. We also have, just so you know, a Future in Space Hangout that's held on the third Friday of every month on this channel, and it's coming up in 2 weeks where we highlight again some of the more general subjects of getting human beings in space, also from members of the double ASs, both of them. So we hope you'll tune in on that in 2 weeks. Okay, so let's get started. I guess we're going to got a lot of things to cover here, a lot of things we want to talk about, and I want to encourage you to leave questions and comments for our guests, and the best way to do that is to use the live chat that I have going. I've got a window up on that right now on my browser, and I'm looking at the live chats coming through, and already some of you are going. So welcome, guys. I want to see and see George and Andrew Planet's with me and a few other people. So thank you guys for joining. That's the easiest way to leave questions and comments, and I will read them out during the hangout as time goes on. Another way to do it is you'll notice I have this thing here on my lower third, Footsteps to Mars hashtag. I'm looking at that on Twitter as well, and so leave a question and comment that way. Those are the two easiest ways you can that you can interact with our guests. And so without any more ado, let me introduce them. So with me is Dr. Dan McNeese. He is a chief scientist at the NASA's Jet Propulsion Laboratory. He works with the people who are trying to get us to Mars. Hi, Dan.
Hi there, Tony. Hi, Harley.
He's also working on the Curiosity mission as well as a great many other things. Also with me is Dr. James Garvin. He's at Goddard Space Flight Center, and he's got his model. Wait, hold it up. There it is. That's his model. Boy, that's the Viking lander right there, folks. Look at that. And he also works at Goddard. He's a chief scientist there working with John Grunsfeld, he said, to help us get to Mars and understanding all of the things involved in doing that. He was also a big person with some of the rovers as well, so we're going to be talking about that throughout. So welcome, guys. Okay, so let's go ahead and let me start with, first of all, this is the 40th anniversary of the Viking spacecraft. Where Vikings 1 and 2 landed on July 4th and the other one on September 3rd back in 1976. We've come a long way, haven't we, with rover technology? Okay.
Absolutely, Tony. It's been a long road, and we have a long way to go, and it's actually quite amazing how far we've come from the days of the first, if you will, kind of eyes wired shut landings to the capabilities we have now with Curiosity, and I think Viking's legacy is still felt today as we look forward. So that legacy is both capabilities and science, and that's the optimism we need to consider sending people to Mars. Dan?
Yeah.
Yeah, it's been an incredible ride since, after 1976 and landing and making all the measurements from Viking, we had a 20-year hiatus with no missions to the planet. Kind of NASA walked away, and boy, when we returned, we've just kept at it, and curiosity is evidence of how much progress we've made.
It came back with a vengeance too. I mean, now it's really crowded in Mars, aren't there? We've got how many rovers are? I mean, is Spirit and Opportunity are they still sending back images? Correct. We also have, of course, Curiosity as well.
Yeah, Opportunity is still functioning. It's a fantastic mission, over a decade on the surface, and we've got Curiosity there as well. We've got multiple orbiters functioning. So it is, as you say, it's a busy place.
Yeah. So we're going to talk a little bit about what we're learning about Mars over the last few years. But getting back to Viking just real quick, what is remarkable to me about what I remember of that mission, and again, this was, oh gosh, 40 years ago. I was well, I don't want to tell you how old I was. But I remember it, and I also remember Carl Sagan was a he was the big proponent of that, and I think they had a pretty ambitious. They didn't know what to expect, obviously, because we had never gone before, but they kind of tried to pack everything into that one lander, didn't they? All kinds of different laboratories to try and find signs of life, and what were some of the things that Viking lander could do, Dan? Or James?
Don't forget there were 2 landers.
I know there were 2. That's right. I know there were Viking 1 and 2. So what were they?
There were 2 landers and 2 orbiters. Let's not forget the orbiters were critical in targeting the landing sites, refining the landing sites, as Gentry Lee would remind us if he were on this.
Yeah.
And also for helping to open the Martian frontier beyond what landers could do. And remember, the landers' goals were to not only measure the surface, but measure the atmosphere as we went down, to observe the surface during at least a Martian year. They exceeded that with factors of 5 to 10, 5 to 8, and to conduct the first in situ extant life biology experiments on another world without all the background chemistry and physics measurements to know all about the environments there. In fact, they were doing it all at once as kind of a treasure trove mission for science, and they were massively successful. Just painted a picture of a Mars that wasn't quite what we expected. I don't know if Dan wants to comment.
Well, I like to think of Viking as the science community trying to hit a home run. They just went all out. The effort to detect extant life on the surface is something that we've almost not dared to do since, because it sent a message when Viking didn't see life that disappointed an awful lot of people. And yet it was a fantastically rich science mission. So what we've done is we've stepped back and we've taken another tact, beginning with the search for evidence of water on the surface, which of course we've found many, many times since, and then of course habitability. Was Mars ever habitable? So when you look back at Viking, they really leapt past a lot of intermediate steps, trying to make that goal of detecting life on the surface.
I think, Tony, if you think of it this way, the Viking view of Mars was cold, sterile, very non-dynamic at the scale of even years of surface observations. And the Mars we know today is a vastly different world, as Dan said, with cycles of energy, water cycles, climate change, recorded evidence of vast sedimentary systems, none of which we had a feeling for at Viking. But Viking gave us, I think, the hope and promise to keep going, and even with a gap, we've come back with a vengeance.
Right, and I guess that's a good argument for you. Just, there's no substitute for being there, right? I mean, you can only look at it for so long before you learn so much about a planet before you.
Would you guys say that it was a Pathfinder, that relatively inexpensive mission? What was it, 12, 13 years ago? That was part of turning folks around in their thinking about Mars, and then leading to the explosion of Mars missions over the past decade.
Well, it was, but lots of people have pointed out that almost every mission, I think you might say every mission that we've sent to Mars, has utterly changed our perception of what Mars is. We end up with a new paradigm with almost every mission, but that started with the early missions, and of course Viking probably hit the ball furthest.
Well, to Harley, I would say the other thing to remember is while we were doing Pathfinder, an elegant demonstration of a new capability, we flew the little Mars orbiter that could, known as the Mars Global Surveyor. which was really
yeah.
the bridge from Viking required that framework that gave us topography, surface temperatures, chemistry, aspects of the seasonal cycle on Mars, the ability to look into the crust with gravity and topography correlations, imaging at the scale of, small golf carts. All those things were revolutions that changed the Viking view to the modern view, while Pathfinder was showing us how to get to the surface cheaper, smarter, better, as some had said.
So my memory of Pathfinder was that was the one that had the big balloons around it and it bounced.
It had airbag.
It was the first mission to use airbags. In fact, that's right. It demonstrated a brand new landing technique with a very small rover, small lander, and then that was followed up with the two Mir landings, the Spirit and Opportunity, which also used the airbags. So yeah, it was brand new attempt.
And then there was the I don't want to say the ditching of the airbags, but boy, oh boy, did they really get from a relatively simple landing mechanism like that to what they did for Curiosity. That sort of took the cake. I remember when we all saw the 7 Minutes of Terror video that NASA produced about what Curiosity was going to have to go through to land on the surface. Now, Curiosity is huge. We have to remind people that this is the largest rover we've put on the surface, correct?
Right. And Tony, the thing to remember is that once we had the confidence, thanks to the Global Surveyor and Pathfinder, to fly the twin Mars exploration rovers, the science appetite increased. And Dan and I and a large community of scientists worked really hard to focus energies on what the next step was. And that step went through the Curiosity rover called the Mars Science Lab, which was really, as John Grunsfeld would say, kind of like a surface observatory for everything you need to know at Mars as you move with mobility to explore this question of habitability. So to put the gear, the instrumentation to do that, we had to go back to the future and reinvent surface analytical measurement techniques for Mars that hadn't been used since Viking in the 70s. And that's required an extremely capable, smart, landed nimbly rover. And so Curiosity is amazing. On day 1270 plus today in a one-year mission, and we're still going strong.
So that brings me to my next question. So Curiosity there's always this thing with NASA where you plan a mission. You say, well, we'd like it to go for, as you point out, a year for Curiosity or 5 years for James Webb Space Telescope, whatever it happens to be. But there's always this hope that it'll go longer. And 9 times out of 10, they really do go a much longer time. So what's going on with Curiosity's current mission status? Is it just going to they just going to run it, and is there funding for that until it stops running, or how does that go? How do people manage this project once it's gone past its designed project life?
Well, Tony, I don't know if Dan wants to.
Go ahead, Jim. That's fine.
Okay. Well, I'll start. Let Dan finish.
Okay.
The process we use is to have regularly spaced senior reviews by external peer colleagues to review whether missions should be extended beyond their baseline mission duration. And Curiosity's gone through one of those. We'll be going through another one the rest of this year to allow it to continue on a second extended science mission. And all of us on the team, Dan and I, hundreds of other women and men, look forward to continuing this legacy of in situ science, following the pathways of habitability, with a mission with lots of life left in all of its instruments, in its mobility system, which is totally amazing, with its power supply, which is incredible, 1,500 watt hours a day to keep her going. So we have tons left to do with this surface observatory. And we have processes that require formal peer review, evaluation, decisions by senior colleagues at NASA headquarters to make those choices, as with telescopes or Earth orbital missions or whatever. So I don't know, Dan, if you wanted to add to that.
Well, let me just throw in that, once you mentioned, Tony, that, these things have just lasted so long, and they tend to last so long. Once you get them at their destination, whether it's on the surface or it's in orbit, and they start working, they really are robust. They've been tested, they've been designed to last for a short period of time, relatively speaking, like with the Mir rovers, 90 days, and they've been going for over 10 years. Once they're up there and working, they're basically bulletproof. So these missions do go on, and as Jim said, there's a process for figuring out how to fund them, but But there's always a competition that's going on, competition between the new missions that are coming and the missions that have been flying for a long time, and it's a science competition. And I think that's really the way it ought to be done.
Agreed. Yeah, that sounds really good. So I want to talk a little bit about getting things to Mars, and then we're going to talk about the rovers, some of the rovers specifically, but as well as and we're going to take this good discussion to go to the future of where we're planning to go with some future robotic missions. But getting to Mars is a pretty tricky thing as far as timing, right? I mean, let's see, the Curiosity rover was launched in 2011, and it arrived in August of 2012, so almost a year later it took to get there. You kind of have to, what goes into planning getting to Mars, whether it's an orbiter or a rover or in the future people? There's sort of, you kind of have to wait for Earth and Mars to get into proper alignment, right? So maybe Dan, you could comment a little on that. What do we mean?
Well, there's an alignment of the planets that works out, so you get minimum energy required every 26 months. And one of the things that Jim and I were central to planning was making use of those opportunities every 26 months, trying to ask a question, get an answer back from a previous mission, and then begin planning the next mission. So what's involved is, first, developing a consensus among the science community about what the experiments need to be. Then there's work on the design. The design includes where are you going to go? Is it going to be dust season when you arrive? What are the characteristics of the environment, fundamentally? And then what you're doing all this time in the background is developing the technology necessary to make these missions individually work. If you're landing on the surface, then, as we've said before, you're inventing new landing systems. The landing system was 4 legs on Viking. We went to airbags with the early landers and rovers, and now we're to sky cranes. So that technology development is also enabling of new missions, and the science for each of them is competed and consensus developed, and we move forward.
I wonder what those meetings are like. It's very contentious to decide what you're going to do next.
I think you could say they're the most fun of anything you've ever done.
Yeah. So, but in the end, like you say, you come up with a consensus. And so, I know I've watched a lot of SpaceX. I'm sure a lot of people have watched a lot of SpaceX missions lately. We're going to these launches for satellites, and they always talk about having a launch window in there. And of course, if they miss the launch window, they can wait a couple of days and get it back again. Because when you're putting something in orbit around the Earth, it's not as big a deal. But here, if you lost a launch window to Mars, you have to wait 2 years before you can go again, or almost 2 years, a little over 2 years, I guess.
Well, Tony, that's right. Or Dan, go ahead.
Oh, that's right. It's a 26-month slip, and that's not easy to handle.
Right. I mentioned that because later this month, in 2 weeks, the ESA ExoMars is going to be launching its. They've got a rover going out as well as an orbiter as well, and it's launching in about middle of this month. And so I wonder if they get nervous about things like that as well. So, yeah. All right. Well, let's go to let's go back to Curiosity a little bit, and tell me a little bit about what were some of the planning that went into that? What were some of the science questions that Curiosity was designed to answer? And I'll let's start with Jim on this one.
Well, Tony, the real thing about Curiosity was as we came out of the era of first wave reconnaissance, understanding the cycles of water, some aspects of climate, a lot of questions remained in the community. This issue of what we now call habitability. How do you find environments that would be habitable by organisms we know and love here on Earth on another world with different environmental conditions recorded in rock records, climate records? How do you do that on another world? How do you find the right places to go? When we put forth the idea for Curiosity, we really sold it as a tandem, the Mars Reconnaissance Orbiter to pave the way with Recon, and Curiosity to follow the guide of the Mars Reconnaissance Orbiter with its instruments to go to the right kind of places. And I think we hit a home run, as Dan said, using the baseball analogy. But so the questions for Curiosity were really, can we access a formerly habitable environment and understand it? Pick it apart geologically, geochemically, measure things definitively. That's a big theme with Curiosity. We have an analytical payload, so we can tell the mineralogy of the rocks, which tell about the histories of cycles of water, how long the water was there, where the water was, where it may have come from. Cycles that we can then measure with the SAM instrument, which is a Goddard JPL French instrument that measures the small amounts of things in the rocks, in the Martian atmosphere. Parts of that are even studying the variability of gases like methane. So the questions are all about the pathway toward understanding whether Mars ever could have been, ever once was alive.
So why do I get the feeling you have a very specific meaning when you're in your head when you say habitability? What are you talking about there?
I'm talking about the possibility of measuring signs of a former, but this is like forensic CSI does Mars. The idea of finding signs in the record of rocks, or even in the atmosphere, of signs of environments that have all the right stuff for producing things that allow things to survive, like microbial life. For example, we need the right range of temperatures, the right radiation environment, the right availability of nutrients, the presence of liquid water for sustained periods of time to allow it to be used by those organisms. All those things, when they come together, can produce a signature in a record of rocks that preserves those indicators. And so that's what Curiosity is doing on the surface with its dozens of instruments. It's picking apart those records as it drives 12 plus kilometers across Mars, which it's done so far. And the results have been spectacular. We've actually proven through scientific measurements that Mars does have habitable environments that were formerly habitable, I should say. That if you stuck microbes there when they were in their habitable state, they would have survived just as well as they do here on Earth. And that's a major step forward in looking for the records of past life on Mars.
So you're saying it was once a very habitable place, not so much now, right? You're saying that not the microbes and the microbial life you're talking about, so far nothing has been found.
Well, we're not looking for it directly because, as Dan said, Viking opened our eyes to the limits of the direct approach. Let's go and start looking for microbes in an environment that's a rather challenging radiation, temperature, set of environmental conditions that life on Earth would not favor. Although in Mars chambers across this country, people can simulate the Mars conditions and show how robust some microbial life can be for exploring those. However, Curiosity is not about the search for extant life. It's about understanding habitability through environments measured through the atmosphere and rock records.
And you're calling those indirect methods. These are ways in which you can say, yes, this would be suitable or has been suitable at some point in the past for these life forms to exist. Therefore, that's what you're calling an indirect method.
Right. It's indirect, but it's the best method we would have if we were on Earth today. Geologists like me, like Dan and others, would go and access the rock record on Earth and make similar measurements to read those past signs of environments on Earth. And we're applying those techniques to Mars with a laboratory that's on Mars, not here. So we've extended ourselves, I think, rather elegantly, and that's the point of Mars exploration. We're on Mars today, Tony, and Charlie and Dan. We know that. I mean, we wake up and data appears magically on our servers. So it's extremely exciting to have that capability today with Curiosity and Mars Reconnaissance Orbiter and Opportunity on Mars.
And so soon ExoMars, that's upcoming. I want to say, well, you certainly want to finish up on Curiosity, but next mission up will be ExoMars. Yes?
Absolutely. Yeah, that's right. There's two components to the European next steps. The first one is a trace gas orbiter. This is the that's coming up that Tony was talking about. It's a Russian launch vehicle. It's a European spacecraft, and some of the instruments are European. Some of the instruments are, in fact, from Russia. And there's U.S. contributions. And this is a mission to go and look for the signatures in the atmospheric chemistry of processes on the surface. And one of those that's most tantalizing, has been talked a lot about in the press, is the possibility of mapping methane in the atmosphere, really looking at parts per trillion detection of methane over the planet. And, of course, there is this supposition that it is geologic, but, of course, there's always the outside chance that there might be a biological source. Then the mission that the Europeans are flying after that is a rover, and they're doing that in a collaboration with Russia as well.
That's right. And so this one, as you point out, was a proof of concept almost mission, where Schiaparelli, the rover they're going to have, is going to set the groundwork for what it's like to land on Mars for them, and to also give them knowledge they need to run a rover on the surface as well. Is there any collaboration between JPL, who we all know is in the rover business, with these guys?
Well, there is, and it's in flux. We've been working for about 15 years on collaborations that have been through all the way from sharing radios and the capabilities that are associated with supporting infrastructure on the surface to experiments. And the missions that I just mentioned, we have a variety of different connections. The upcoming rover from ESA is not one where we have a part in building the rover itself, but from Goddard there's an instrument that's going to make measurements from the base platform, which is the rover itself. I don't know, Jim, you want to mention something about MoMA?
Well, I did, Dan. In fact, Tony, the excitement of this partnership, which we really find incredibly enticing for enhancing Mars exploration, is it allows colleagues across the world to work on instruments together as they have on Curiosity. Here at Goddard, in collaboration with France and Germany, we have an instrument called MoMA, which is a true molecular analyzer.
MOMA?
Pardon?
MOMA?
MOMA. It's the type of device that will allow us to measure complex molecules, including those that would be formed by biology, large, complex organic molecules, high molecular weight, in a way that's even more refined than the instruments we have on Curiosity. What makes it special, as Dan was getting at, is the ExoMars 2018 rover also carries with it a 2-meter deep drilling system that can access deep enough into the Martian surface covering rocks and soils that it can get beneath the depth of penetration of ionizing radiation and get into a zone that's really not been tapped before unless it's exposed by some dynamic process, an impact, a scarp that collapses or something. And those areas, we believe, will be the most fertile places to look for preservation of organic molecules that would be complex and big. In a radiation environment, those molecules will be destroyed, and that will make them very difficult to be understood. So by partnering with our colleagues in Europe and working together, JPL, Goddard, lots of colleagues, we can extend what we're learning with Curiosity to a new type of mobility, a subsurface mobility, which many of us think will be very exciting.
Okay, well, I want to get to some of your questions. You guys are starting to do quite a bit of chatting there. I'm glad to see that. I'll get to your questions in just a minute. I also want to get into a little bit of the future plans for going to Mars with rovers, as well as what sort of stage this is setting for us to put human beings there. But you said something earlier, Jim, that I want to go back to, and that is, you said that Viking taught us the limitations of a direct measurement for life, and I guess I'm not getting why that's. I don't understand why we don't want to just look directly. Are we just assuming there isn't any life there now, and looking for it directly is pointless? What did you mean by that? I guess I'm not sure I understand that.
So Tony, maybe I'm a geologist, so forgive my rocky nature, but but let me put it to you this way, as best I can, in the spirit of Jerry Soffin and the biologist that got us going so long ago with Viking. Tim Much, my own mentor, one of my mentors. The direct search for life in an environment that has a land area even 1 millimeter thick, as large as the continental landmass of Earth, is a rather difficult search. You know, if you thought of doing a Google search and you said car and you got 100 billion hits, you might not be that refined. So understanding how biology, living biology as we understand it here on Earth, would work on another world with different environments, different chemical reaction pathways at different rates, with different changes of environments, is a big question. It's hard. It's hard to do that on Earth, where biology is in a state of revolution today. The microbial universe, as we say, is emerging as we get to know things that when we started with Viking we didn't know. And so that biological revolution down to nanoscales shows us how hard it would be to look directly for life unless we saw a geologic environment, an active environment today that had all of the right stuff. Warm, wet, fuzzy, protected, all the things where life would get a foothold, a toehold, a microbe hold here on Earth. So we're looking for those with orbiters like MRO, like future orbiters we'd love to fly. like
Oh, okay.
ExoMars, as Dan said, sources of trace gases that are in disequilibrium in the atmosphere. So leaping right to one place and saying, let's look for the Martian microbes, or whatever they would be, is almost premature before we understand the record of past life.
Okay, so to use maybe a rather oversimplified example, and correct me if I'm way off base here, but the way what you're saying is to me is that you don't want to just jump in and start looking for life right away anywhere. You want to narrow down where your places would be where it would maximize your chances. So, for example, even on Earth, where we know there is plenty of life, and you wanted to see if there was life here, and you landed a rover, let's say, in the middle of the Mojave Desert, and tried to do some scoop sand samples, you might not be the best place to try and find life as if you had chosen, say, the Amazon, where you're almost much more likely to find it. Am I oversimplifying things a little bit, or?
No, Tony, that's good. Look, it's all about location and understanding the location.
Okay.
So, like planning a vacation, you can say I want to go to an island. Well, there's 20,000 islands on Earth. Which one?
Got it.
When you're looking for life, you want to put together the fundamentals. And Vikings said, let's go to the best places we can, see what we get. Great first step. Opened our eyes to the complexities of this wonderful
Didn't hurt to try. Right.
Now we're ready to go to the next step, which is to follow the different pathways. And that's what Dan and I in the community have been doing for the last 16 years in earnest, but really since Viking.
Well, let me jump in, Tony, and just
make
another point on this subject. One of the characteristics of the exploration of Mars that we've been careful to protect is avoiding the yes-no answer of the search for life. You land, you look for living organisms, you don't find them. What you know is you haven't found them. You're not proving they're not there around the corner. You're not proving they're not there deep in the subsurface. You've just answered the question for the measurement you've made. What we need to do is to build up the scientific understanding of that environment, to sneak up on the question with knowledge that will then allow us to do the experiments that will be fundamental to prove that life's there. And that's not trivial. In fact, the conclusion after all these years of work is that you're going to have to bring pieces of Mars back to Earth to really prove that there's life there or not, or whether there was ever life present. It's not going to be possible to do that with measurements made at the surface.
So what the rovers and what MRO and all the orbiters and stuff that we've got on Mars are currently doing is what Jim mentioned earlier in the Hangout, which is that you're building the big picture for habitability. That's what you mean by that. This is how life should live on this planet if it is in fact there. And why though? I mean, okay, I get it now. You don't want to just, look in one spot, you don't find life, okay, that doesn't mean it's not deeper, it's not somewhere else. I understand that part, but why now are you saying that we have to bring it back? What if all that's going to say is, well, there's not life on that piece we brought back, right? I mean, you're still kind of doing the same thing, only you're bringing it back to Earth to say that, right?
Well, remember, we're not looking for extant life. We're looking for the conditions in the ancient past, 3.5 billion years ago, that might have supported life. And then we're looking for the constituents that might have been necessary to produce life. And, I don't think anybody on any of the teams that are currently planning imagines that we're going to be bringing back fossils. No, this is an experiment of biology at its most elemental level. It's really one in which one does measurements in the laboratory that you would do in order to stake out the territory for future searches.
Okay.
And Tony, if I may add, I think, again, think of this as a forensic question in detective fiction. So we want to read the records, and we have to understand what records we want to read. So the first step, as Dan said, is to find them. We're getting good at that. Curiosity and the Mars 20 rover coming up, ExoMars, are going to prepare the way. Once we have the good stuff, that sweet, high-grade material that we think is most possibly containing signs that could be even indirect signs of past life, we can bring them back to the massive array of Earth laboratories that today can pick apart things at parts per trillion and look at stuff that even at the time 20 years ago we wouldn't have imagined doing.
I see.
So that allows us to expose all those bright women and men and all those laboratories across the country and the world to the problem. And so a nanogram from Mars in the right place could tell us, yes, complex organics. They evolved in an environment maybe they are the building blocks of past life. That's the detective question. Once we see that, by bringing samples back to Earth, then we can ask, okay, knowing that, where would we look for extant life today if there's any chance it existed? And that's the logic that Dan and I and large numbers of the community have been working toward, not the direct, let's hit the home run and hope, it's a high fastball and we can get it out of the park. Let's open our eyes to the fact that Mars, as many people say, does not follow our textbooks. So we have to learn the Martian textbooks.
Well, I have. This is really helping me. I spend most of my time looking at deep fields and distant galaxies and gravitational waves and understanding large-scale structure of the universe. So these are questions that I love having somebody who's out there on the running these rovers, looking at the planets closer by, so that I can pick your brains on this. And this is stuff that I've always wondered about. I never understood why we weren't just testing for life right away. And you made a good case for doing this other stuff. So we have things like MAVEN, MRO, the Mars Reconnaissance Orbiter. These are all in orbit around Mars, doing work on the atmosphere, the topology, the high-resolution imaging of the surface. We've got rovers going down, drilling into rocks, telling us the composition of these different things, all in the request, among a great many other things, to learn about how habitable life is. And I guess my next question, before I leave the current state of rovers and orbiters and go to the future, I want to ask you, in your careers working on Mars and looking at the data from these various missions, what is there anything that's that you found most surprising? And I'll start with you, Dan. In all your years working, was there anything that surprised you the most?
Well, I believe that a recent result from Curiosity is really the measurement that we really began hoping that we could make and learn from, and that was proof that there was actually a body of water sitting on the surface of Mars for perhaps millions of years, a lake, possibly a very, very large lake, that would have sustained life if life had started on the planet. In other words, the true liquid water, wet, warm environment that we've never been able to prove with real confidence exists, and that measurement was made within the last year.
Yeah, we heard that.
It was published in Science Magazine. It was led by a team. The leader of the team, in fact, was John Grotzinger, who was the past project scientist for Curiosity. It's a fantastic step forward. That's the most exciting measurement that I think's come from the whole of the exploration so far. I don't know what. Maybe I've insulted you, Jim.
What about you, Jim?
No, Dan, I think, if I may, Tony, I think there's two that have me gripped. I think one was the emergence of this modern water cycle on Mars that we first saw the glimmers of with the Mars Global Surveyor, with hillside gullies that first were just a few. I remember the PI telling me at a meeting, don't tell anyone, we see a few of these things. And we said, okay. And next we know there's thousands. And now we see ones that are even active. We give them interesting names like recurring slope lineae, but they're effluents of what we believe to be fluids, in this case possibly salty, that run down hillsides that show a connection between the liquid water story on Mars and the surface, where present conditions are not so favorable. And the second one, it really builds on what Dan says. We found this evidence of standing bodies of water that persisted. We've also recently found and published records of organic molecules on Mars from Mars. Not life, that's organic molecules.
The building blocks, so to speak.
The building blocks. Now, geology can work toward making organic chemistry. It's wonderful stuff. Very challenging for those of us that are geologists to understand. But nonetheless, we've done that now with Curiosity as intended. And so Curiosity, thanks to people like Dan said, John Grotzinger, the PIs like Paul Mahaffey, has really rewritten those textbooks. We'll never go back now that we know these things.
Awesome. Okay. Well, gosh, I can't believe how much time is going by. I want to show a couple of images real quick because we were talking about this before the Hangout, and I think Harley, you've got a couple of them queued up. There's an image that Dan told us about that's just from Curiosity just this morning, right?
Yeah. This is an image from Curiosity looking across the dunes toward Mount Sharp, and this is the destination that we've had from the very beginning. We've traversed a lot of very, very complex terrain, learning a lot about the geology, and the goal is to get up on the flanks of Mount Sharp and to begin making measurements. In fact, that's what we've been doing. I think, Jim, it's about the last 6 months we've been actually making measurements on the flanks of this mountain.
Absolutely, Dan. We're climbing the slope. We're adapting as we go, making measurements, drilling rocks, exploring giant, massive sand dunes. The Bagnall Dune System, as Dan described, named for the pioneering physicist who studied dunes in the 40s in the Second World War. We've studied them up close in a whole campaign, and we've also developed new techniques as we go, better ways of letting scientists do their work with new softwares on the rover. We're post 12 kilometers of driving on Mars in the 1,200 plus days we've been going. So,
is this true color, Jim and Dan?
Yeah, I think it's very, very close. I think it's as close as the camera team can make it. The processing isn't complete because these images are available online in their raw form, and that's where this one came from. Is everybody able to see this, Tony?
Yep, I've got it up on the screen.
Okay.
And remember, guys, what's so exquisite about this, the Curiosity rover has more than a dozen camera systems, and several used to keep it safe, several used to drive it so it doesn't run into things, brilliant techniques. Also, the science cameras allow us to look out at the horizon with telephoto lenses, inspired in part by some of the desires of Jim Cameron, who was affiliated with the imaging team. And I'm on the imaging team, lucky enough to have use of these things. We also have cameras that can look at 10 or 15 micron resolution at the textures of rocks before we drill them, looking for other signs. So we're a very visual mission with the imaging we can do to go together with the analytical measurements we make.
Yeah, well, in addition to that, to the science you're getting out of it, it also helps capture the public's imagination as well, all these beautiful pictures coming through. So,
if you want to, you can look at 100 images from today online. If you go to the JPL website, look at Curiosity Images, you'll be able to see images from every day of operations, and you'll be able to see at least 100 from just the last 24 hours.
Yeah, and another image that I want to show everybody that came out was, I don't know if it was this week or last week, but it was from Maven. Took a look at one of the moons of Mars, correct? Do you have that up, Harley?
I'm bringing it up now.
Yep. And this one was from, this is from Phobos.
You got it?
Yep, it's up.
This is an image of Phobos, one of the two Martian moons in approximately equatorial orbit, and it's captured by the Maven mission, whose job it is to explore how Mars loses its atmosphere through interactions with the wind of energetic particles from the sun. It's Bruce Jakowski's mission. So Bruce won a mission through a competition to do this brilliant thing, and his mission has the flexibility to use its ultraviolet imaging spectrograph to also image objects like Phobos, which are of great interest not only scientifically, but also as possible destinations for first human access to the Mars system.
All right. Well, so there's a couple of things we've got going on just with some of the probes that are out in recent news that's going on. It's a very active place. Now you mentioned that. So I want to talk a little bit about what are our plans going forward, and are there any? What are some of the big missions that NASA has planned for in the robotic realm for going to Mars? I'm not sure who the best person to ask was, so maybe just either one of you can pipe up on that.
Well, let me talk about the next mission that's waiting in a hangar, if you will. We're next going to be landing on the surface with the InSight mission, which is a mission to explore the interior of Mars and to relate that interior to those of the terrestrial planets, trying to understand better how terrestrial planets formed. But that mission has been delayed, that 26 months we were talking about earlier, because there was a problem with one of the instruments, in fact the seismometer, which is the key instrument for detecting Marsquakes and inferring the structure of the interior. So that's the next mission to go, and we're excited about getting that mission all put together and ready to launch in now about 24 months.
Okay, so I was going to ask you that next. All right, good. So that's next. We've also got ExoMars on the way. Dan, did you want to, or Jim, did you want to add something?
Well, I wanted to say, and Dan did a good job. InSight is an essential way of comparing the terrestrial planets through their interior structure, and also by measuring something called the heat flow. The geothermal gradient for planets is like a fingerprint for how their crusts evolve. We know it for the Earth, the Moon, really well. We really need to measure it for Mars to put these planets together. But the next big mission, Dan and I were fortunate enough to work on some of the antecedent work for it, is another rover whose job is even tougher than Curiosity's. It's a rover that's the first leg, if you will, of the campaign for sample return, to bring back samples relevant to the quest for life on Mars. That rover, called Mars 2020, not the most original name yet, but trust me, young women are better than I. But that rover is in development at JPL with an international array of instruments. Literally, I'm passionate about what it can do because it will lay the groundwork for collecting things that our intention is someday to bring back to Earth.
So I take it the name is sort of implying a little bit about when this might happen?
Right.
Sort of. It's a way of making sure it does happen in 2020.
Yeah, good.
Dan's right.
So Mars 2020 is going to, you say, lay the groundwork for sending things back, but it's not going to send things back.
It will collect the samples through an interrogation, a triage process of exploring the immersive Martian geologic terrain, collect samples and cache them, protecting them for the time before they are returned to Earth. And it will collect up to dozens of these samples of the best materials we can see with a whole new array of instruments that can look for signs of organic molecules, elemental chemistry, which is how rocks put themselves together, mineralogy, put them all together like a detective toolkit, cache them, and prepare them for their trip back to Earth from a future mission. And this interrogation is critical, Tony and Charlie and everyone, because Curiosity's sort of shown us what to do. This mission will bring it home and actually start that step.
Very exciting. That's amazing. Okay, well, I'm going to start getting to your questions finally, folks. I'm sorry. This conversation has really got me going, so I have a lot of things, but I can't hog it up. I'm going to start with Andrew Planet on Twitter. He's going, and I'm going to expand on this question after I read it, but he's going, is the possibility of finding native life on Mars stopping us from seeding it with Earth organisms like bacteria and fungi? And so before you answer that, I want to add also to that, we've already talked about how busy Mars is. A lot of stuff is there. I know that with Viking we did some work on making sure it was decontaminated. I want to talk about this idea of seeding Mars with organisms from Earth, and how worried and how good of a job have we done that we haven't already contaminated it with our own spacecraft.
Well, let me start. So there's a protocol, planetary protection, and this is taken extremely seriously by NASA and everybody else that's sending devices to the planet. And what we're doing is protecting Mars. We clean the equipment. It's sterile. It goes to the surface. It makes its measurements. It doesn't leave biological organisms on the planet. The steps that we're taking to return samples involve making sure that we don't do any round trips as well. We're particularly careful about cleaning materials that are going to be returned so that we don't do any false positives, carry something there, bring it back, and supposedly detect life, get it wrong, it's actually from Earth. These protocols are constantly under review. International teams are studying ways of keeping things clean. And I've just got to say that the protocols are pushing us forwards to get these really absolutely pristine samples back from the planet.
But just to reiterate what you're saying now, right? So this is an international observance, right? So right now, with the Europeans sending something out later this month, they are following the same protocols. The Russians, all the people are following the same protocols, regardless. Everybody is.
Absolutely right. They're all signatories to the same rules.
Okay, so we're not sending any out there, and obviously you're saying, then. So Andrew, I guess that sort of implicitly answers your question about, is it stopping us from seeding it with Earth organisms? Seems like seeding it with intentionally is exactly the opposite of what those protocols want. So
well, and Tony, if I may, this is Jim.
Yeah, sure.
We can recreate what we understand of the Martian environment here on Earth. We have Mars chambers at JPL, at Goddard, at other universities. And then we can introduce extremophile life, microbial life that can handle harsh environments, and see what happens by doing the fundamental biology that's important. And those experiments are being done here on Earth. We don't have to go to Mars and possibly ruin the very thing we're trying to understand about another world by seeding it. We can do those explorations here, and that's phenomenal because of what we've learned from the Mars exploration program. So,
well, what are you finding out? This is amazing. So what are you finding out? Is it easy to do? I mean, if you can, does life pop up if you give it some in the current Mars chambers, or is it pretty difficult to get going? What's the answer?
Well, I don't know the full spectrum, but what has been done so far is there have been experiments where extremophile microbes, things that would live in very harsh, cold, salty environments, for example, introduced under Martian conditions, don't all perish. Now, it doesn't say they thrive, and more work across the astrobiology community needs to be done. Michael Meyer and the leaders of that program, Mary Wojtek, can talk much more about that than I. But the fact that we're starting to understand what they do when they're introduced into this type of environment, the Martian environment, is exciting. And it will prepare the way for us to be smart about sample return, as Dan said, not introduce the false positives, bringing Earth to Mars and back, because that's something that's a very real possibility, and hence we have these protocols.
Okay, got a really good question here on the chat window from the Viking Preservation Project. Let me ask this one. They're asking, can you address how heritage technology, this is the building of the body of knowledge, helps to offset costs for current missions? Ablative techs, you're giving some examples. Aeroshells, throttleable engines. So what? How is what's been built before? Is it saving us any money going forward with building with Mars exploration?
Well, every mission builds on the technology of the past, but perhaps the best example is the one we've been talking about going in this large rover, which is called, the 2020 rover. This is a Curiosity rover with a Curiosity landing system, all of the software and hardware that can be inherited, but the science instruments have been changed out. So you actually are multi-purposing. You're returning to a technology in large part to save money, but it's also proven technology.
Well, sure, and you also want to make sure you're using the latest detectors and the latest computers and all of that too. So you want to use the newest of technology that you can get your hands on while building on stuff from the past. That was a good question, though. George,
there's another aspect of this we have to remember. Sometimes we use the information we get, as Dan said, in the pipeline, to fundamentally change how we explore and to save money in exploring. For example, with the Global Surveyor, we measured the global topography of Mars in an absolute center of mass reference coordinate frame, giving us basically the ability to land by understanding where the ground was very precisely. Prior to that, the uncertainties were thousands of feet, making the engineer's job, who do a great job, by the way, very difficult. But the legacy of that information purely is something to help us land better and smarter. Bigger things like Curiosity, like Mars 20, is part of the way in which we build on that past. And that's something where the knowledge, definitive knowledge, prepares the way.
Yeah. So George Caldwell, he's asking a couple of questions on the chat window. One of them is, what is the aim of the Mars 2020 mission? We talked about that briefly already. That's going to be laying the groundwork for return. It's going to be building the samples, and Jim was telling us that this is going to be getting the stage set for sending things back from Mars. And he's also asking a little bit later on, or a little bit before that, what happens to the rovers on Mars after they finish their tasks? Do we do anything special with them, or do they just get turned off? What happens to the rovers? And for that matter, the orbiters. Does anything happen to them?
Well, we run them to death. How about
yeah, that's right. You run them ragged.
But there's, sometimes an instrument will continue to function, like a weather station. This happened to the Viking landers. The weather stations continued to function long after most of the other equipment had given up. And that's happened on all of the missions so far. You kind of see degradation occur, and then finally a critical piece of electronics or perhaps battery goes and you lose contact. And they become sort of, if you will, a signpost for future exploration. I think one of the greatest things about a movie I love, The Martian, was going back and visiting the the rovers of the past. It was fantastic.
Oh, I know. I have similar daydreams about that with the moon. If you go to the moon, could you imagine going to the Apollo 1 landing site, or just some of that? So yeah, that was really cool to see that in The Martian too. Well, let me ask you while we're talking about it, what did you guys think of the movie? I'll start with you, Jim.
Well, I enjoyed it thoroughly. I found the physics of dust storms at the surface of Mars fascinating. I'll leave that as an exercise to the atmospheric scientist. I see Dan chuckling. Just imagine the high school physics question there. But I think really, in the spirit of exploration, the movie did a great job. I guess my thing really strongly to say is, if only we had the hardware capabilities that those people had in the movie, with gigantic spacecraft to carry our people, women and men, to Mars.
Those were huge. That's true.
Yeah, gigantic Mars ascent vehicles that would be something Dan and I would salivate over if we had, for sample return. So I think the projection forward of what we'd like to have was fantastic, and I think it depicted NASA and JPL, in the can-do way that really is the way we've explored Mars for the last 40 years and more, really, back since Mariner 9. So lots of fun. Good job to Matt Damon. I like the fact that they had to paint the sand to give it the Martian ochre color. That's always good. Who wouldn't like that?
Okay, Dan, what did you think? Did you like the movie?
Oh, I really loved it. I thought, if you've got to have a disaster occur on the surface and you don't want to twist the physics too far, Jim, it's a heck of a lot better than having a monster creep out from behind a rock. So I forgive him the physics errors on the atmosphere and the force of the winds, because I just thought it was a good way of introducing that sense that there's high risk, and you needed a rescue in that movie to really give it some pizzazz. So I think we all have to give a nod to that.
Well, I can't believe I'm already out of time, but I'm gonna just keep going a little bit longer here, if you guys don't mind. This brings me to a question that Dan just brought it up about the atmosphere of Mars and its relative thinness. You had mentioned earlier, Jim, that MAVEN is studying the atmosphere and how it's slowly being eroded by the solar wind. Mars doesn't have a magneto, does it? It doesn't have a magnetic field, right? It's basically a geologically dead place. Am I right in saying that?
Not geologically dead, Tony.
Well, by that I mean there's no tectonics, there's no plate movement.
Tony, that's not true either, sadly.
Oh, good. I'm glad to hear. Then please expand.
Strange ways. This is a mystery tour of geology. But no, Mars is a planet that we think had a magnetic field, perhaps Earth magnitude, an internal magnetohydrodynamo, and it lost it. How do planets lose things like that? I lost $1 the other day, not a magnetic field. And so that's the question. And Mars Global Surveyor unearthed that possibility, and future missions will conduct further work, and MAVEN's doing that now, in fact, and so will ExoMars, to understand how do planets do that. And then protecting Mars' atmosphere over time with no magnetic field is a challenge, as Bruce Joukowski's MAVEN mission is showing. So these are the big questions when we compare our planets in this little solar system, and why Mars is so important.
Well, is Mars going to lose its atmosphere over time then, because it doesn't have a magnetosphere?
And
any protection from the sun?
It's losing its atmosphere with time, which is what MAVEN is measuring. But the largest loss of the atmosphere occurred about 3.5 billion years ago, when the planet went from a wet, warm environment to an environment which is like we see today, where the pressure is about 1/100th of what it is on Earth. It's very cold. No liquid water can be sustained unless it's a brine, perhaps, on the surface. So it's a very, very different place. And yeah, the loss of the atmosphere is a continuous process.
And so let's bring this back to what it means for humans to go there, because the magnetic field of the Earth is vital for us to be able to live here and for life to thrive like it does, in addition to the different layers of the atmosphere that we also have protecting us. Mars doesn't seem to have any of that going for it. It seems to have an atmosphere that's going away over time. It doesn't have a magnetosphere to protect it from a lot of solar wind, the solar particles, charged particles coming at it. So that means, right, that we have to build that into our missions. We have to harden everything. We have to protect the astronauts, or the Martian nauts, or whatever we call them, that would go there, right?
Well, Tony, I would say yes, and people are tough and tenacious. And we want to go.
But not susceptible to, I mean, we can't just take a complete bombardment from the sun all the time. We have
Well,
to.
indeed, but thanks to missions like Scott Kelly's recently completed mission, we're starting to get to know how to live and work in space, and by watching how we explore with our rovers, we're training ourselves onto how we'll be better explorers when we have the tools to open that Martian frontier to people, and also to protect that Martian frontier, as Dan said, from what we will naturally carry with us. So I'm bullish on us getting there and being there, although I would say to many of us, we're already there with our rovers.
Okay, and so there'll be a couple more comments before we have to go. The Viking Preservation Project is saying ExoMars is the next phase. Studies needed to leapfrog the current studies, and the collaboration is the key to future missions. Hank Moore of Viking said, if we could just drill down 1 meter. And this is bringing to the point that Jim brought up too about having a super again, not a super drill, but a drill that can go down a lot further than what we currently have. All right, guys. Well, there's a lot of great questions, a lot of good comments. I want to let me just make sure if there's any, because I have a question I want to leave with. Protocol started with COSPAR in the 1950s. That's another comment from Viking Preservation Project.
That's right.
Yep. Let's see. How is it that after all the money spent and all the probes that have been and will be sent to Mars that we have never sent a return sample back to Earth? That's a good question, actually. It's from McMadman51 Canada. Nice handle there. So yeah, why haven't we done it up to now? Is it what's the engineering challenge of bringing back a sample, Jim?
Well, it's really 3 things. Number one, knowing what samples that you want to collect to bring back. So we're working that. Next, it's actually getting those samples protected well enough to follow those protocols and blast them off the surface of Mars with a rocket with enough energy to carry them to a Mars orbit position for rendezvous or a more distant position, and then return them to Earth safely and enter the Earth's atmosphere and land without any risk of contaminating Earth from that. And so that round trip travel to Mars has only been done to one other world in the history of women and men, and that's to the moon with people. So Mars sample return is kind of Apollo without the astronauts for science, and also, as Dan and I and others believe, as a pathway, a stepway to putting people on Mars as explorers, as we saw in the really engaging movie The Martian. So there are some big technology steps that our engineers are ready to take, but they take time and money, and that's why Mars sample return has been so tough.
Okay, and
sample return is about 5 missions in one, if you put it bluntly about why it's so hard. This is a real challenge, and we're building the technologies. We're getting ready to do it.
How confident are the two of you that we'll be able to get a human presence there? I think NASA's been tasked by the president to get there by in the 2030s. How confident are you guys that we can get there, based on your experience with working with Mars missions?
It's funny. I was asked by one of the presidential commissions when I was a young man sitting in a little panel. When did I think that humans would arrive on the surface of Mars? And I said, well, you know, I think my colleagues would disagree with me, but I think it'd probably be as long as 2025. And everybody in even the committee went, we've never heard a more pessimistic statement from a young man in our lives. This is an impossibility. How is it that NASA has convinced you that it's so incapable? So let me say to you, with that background, I think the mid-30s is possible, but you have to have the will. And I think it has to be a universal will, international commitment to do it.
I was going to ask you that next. How important will other countries be in this effort?
Critical.
Yeah.
I don't think we're going to do it alone.
It's really it's just too expensive for one country, perhaps, to try and do this whole thing.
We're going to be covering those possible scenarios and international partnerships in upcoming first Friday of every month Hangouts.
All right, that's exactly right. Okay, well, let me get to my final question, and I'll let you guys go. And I want to thank you for indulging me, because this is a fascinating topic. But I've often argued that I think if we ever find life on Mars that is independent of that actually was from Mars, didn't come from Earth somehow, or wasn't a contamination of some of it. But we determined that we find Mars, life on Mars, that I've always argued that would be a bad thing, because that means that life is probably very, very common in the universe. If we could find it independently twice in the same solar system, then life is probably a very common occurrence throughout the universe, because it happened twice in our own backyard. And I think that speaks badly, because that would mean life is teeming everywhere and we haven't seen it yet. So where is it? What do you guys think of that? Would you be excited? Would it be good news to you to find life on Mars that has been independently verified to have actually come from Mars, or at least in the past?
I mean, Tony, come on. That would be...
Uh-oh, I lost... Dan just hung up.
Yeah, he doesn't want to hear Jim's answer.
Sorry, Dan. But I guess I would say seeing signs of life, of Mars life, not from Earth, would be the greatest thing since crunchy peanut butter. Come on.
It would be big news. I'm not arguing that.
Your point is well taken. Why shouldn't there be this magical chemistry that is life, as we understand it here on Earth, everywhere? Our tools for detecting it are so primitive that we really have to get real about that. So I'm bullishly optimistic that our tools, as we evolve them through Mars exploration, the robotic program, someday with people, is going to tackle that problem. And if we find it, hallelujah, there's the Super Bowl win. Let's call Beyonce and celebrate, because
very happy. Okay, I'm glad you're back, Dan. I thought I scared you away with that question. I thought you were like, I'm not answering that question. I'm out of here. So, what do you think? Is it good news? Would you be happy if we found life on Mars? Would you look at that as a good thing?
I think it's an answer to the biggest question that exists. I think it's the ultimate question. Are we alone? That's it. And I think having opened up now what we see as a vista of exoplanets, that question will just drive us on and on.
Yes, well, I agree that it would be the single biggest thing we have, the history of humanity, to have discovered. But I've also argued that I think it means a little bit bad news, because I've been trying to grasp with this thing called the Great Silence, or the Great Filter, and I think that if we find life on Mars, then that would indicate that the filter, whatever it may be that's keeping us from seeing other civilizations, may yet still be in our future, and we have not passed it. What do you think, Harley? Would it be good news for you?
Terrific. Terrific.
Yeah.
I think my two colleagues, Dan and Jim, said it better than I could right now.
All right. Well, I'll leave it at that, and I want to thank everybody for leaving your great comments and questions. I'm sorry I didn't get to all of them. We only have an hour, and we've already gone past that. So I just want to so Dan McKees and James, Jim Garvin, I appreciate both of you for taking time out to talk with us about these future Mars missions. I hope you'll come back and give us some more updates as we get more things out there, and as more gets learned about Mars from these missions.
Count us anytime, Tony.
Okay, great. Thank you very much. And as Harley mentioned, we will do our future. We will be back next month talking about the next other parts of getting to Mars. Do we know what the subject's going to be about yet?
We don't know exactly. I think we're going to be looking at. I think we'll be talking about some of the key technologies for getting humans to Mars, and why do we think that they are in hand, or at least not too far out in the future.
Okay, great. All right. Well, we'll see you guys next month. Also in 2 weeks, our Future in Space Hangout. We'll see you there on this channel. I want to thank you all for watching on behalf of all our guests and for Harley Thronson. Thank you all for watching, and as always, keep looking up.